Mitchell. I'll be leading the next chair. Mike, do you have anything to say before we transition here?
No, not at this time, but I want to thank everyone and all the speakers from session one that had presented today. Very great information. Thank you so much for sharing.
And thank you on my part. Thank you so much for keeping the time.
Absolutely. Some great stuff ahead of us here. Without further ado, we'll have 6 presentations to go through. They will be 10 minutes each, and then we'll be followed by our lunch break. So again, thanks to everybody who presented before, and looking forward to these. We have first up, Peter Meyer with the Bureau of Labor Statistics. Hi, Peter. Are you there?
Thank you. Yeah, am I audible?
Yep, I can hear you.
All right, hi, I'm Peter Meyer, and my co-author is Kendra Asher. We're using industry and occupation data over long periods of time for BLS productivity statistics, and we use imputations, which we are trying to improve. Next slide, please. Our data of interest are from the Current Population Survey, or CPS. The survey collects information from households about the jobs that people have. The unemployment rate is computed from that information. The survey is monthly, and it has been pretty consistent for decades, and it has been used in a lot of economic research. In the Productivity Statistics Office, we're using it to calculate, to track changes in the workforce of each industry, because that's associated with changes in productivity. For those indexes, we need long, reliable time series for industry over the decades, and we're trying to bridge smoothly over industry and occupation classification changes, especially a big change in the year 2000. It's common to make crosswalks or concordances from these categories. But in this talk, I'll describe a new larger scale approach that uses microdata on each respondent. And that should be more accurate, but it's technically challenging. Next slide, please. The respondents told the survey collector about their employer and their job. Coders at the Census Bureau then classified that information into an industry and occupation. I've interviewed several of those coders. They assign industry first and then an occupation that makes sense with it. We will be imputing industry and occupation jointly too. Each of those is recorded as a 3-digit code. There are over 200 industries and over 400 occupation categories in our period, with changes in the classification usually associated with the decennial census when they define a new industry and occupation classification system, or did then. For long-term comparisons, we want to harmonize those. One reason people do that is to watch how things change over time. For example, the big changes associated with increase in computerization, which resulted in growing industries and occupations, and the splitting of the electrical engineers category and the creation of more and more software categories. In the COVID era, this kind of information is used to estimate how many people can work from home. These classifications are used a lot in research, not necessarily to study specific categories as we do, but rather to hold them constant in a study of something else like income distribution. Next slide, please. A standard approach is to match whole categories from one period to the next period, and that leads to a kind of table that maps, let's say, old industry 110 to new industry 107. And all people are mapped then together. Those crosswalks are often good enough, depending on the research question, but they miss detail. One problem is that they create empty cells. If you're translating from data with 200 categories into another one with 3 destination set, which means the time series have breaks. And starting in the year 2000, there were more precise industry definitions than before. So some such breaks happen right then in our CPS data. The presence of empty cells also implies that the time series you get are biased because they're systematically grouping jobs together in one period that would have been separate in another period. To avoid that problem, people might group the small categories into larger ones, major occupation groups, let's say. And that can be fine, but it might lose the precision that was needed for some research questions. And there is a buried literature about these trade-offs. Researchers will often grab something and use it, but we could make all those research findings a little more accurate if we can fill in more accurate and precise industry and occupation data. There are special cases in which we can definitely do that. I did a study of lawyers and judges, which are combined in some censuses and separate in others. A logistic regression can predict whether a person in a pooled set of lawyers and judges is a lawyer or a judge based on employer information, income, age, and education. It's not perfect, but it gets past the problem that in a pure crosswalk system, the judges category might be totally empty in some years. And it's kind of fun to study it, but it's much too time consuming. Realistically, we cannot take a week to study each occupation or industry and think deeply about it to make precise imputations. Next slide, please. So we need to scale that up. There are good data and methods for this, some of which are new, certainly new to me. There are special data sets in which the census coders applied both the 1990 and 2000 classifications to the data from the same respondents. Those are called dual coded data sets, and we have 2.4 million observations from 2000 to 2002 in our dual coded data set for that period. In this effort, we're going to train models on that to impute the Census 2000 definitions of industry and occupation to the 1986 to 1999 data. The target data set has 15 million observations. My colleague Kendra figured out how to do this using R and the Ranger package. It uses a random forest statistical classification modeling method. It sets up rich, complicated decision trees on the dual coded data set using many predictors to classify the industries and occupations, to predict the industries and occupations in the dual coded set, and then combines the results of all these trees. So it's building a giant Rube Goldberg machine to make each prediction. Next page. We fill in several variables using the Census 2000 definitions on this earlier data up to 1999. These cover whether the employers in the private sector or the government or nonprofit or self-employed, and how many hours this person is working on the job, then occupation and industry categories. We also need to impute a NAICS industry, which is different from a census industry. We can't summarize the prediction, the predictors, the effect of the predictors in the way one would for a logistic regression, but we do have information on which variables were useful predictors, and we can check in various ways whether the results make sense.
3 minutes.
The model is trained on a portion of the dual coded data set, and then we can check its accuracy and the significance of various predictors in an out of sample way on a test set that is within the dual coded data. As expected, the strongest predictors of industry in the dual coded data are associated with the job itself, occupation and industry in the native category system, the original category system. And variables related to the location of the worker and the demographics of the worker also help. Every CPS observation has values for those variables, but one complexity is that we can't use the whole target period data at once because there are changes in the definition of some predictor variables over time. So this is a long program which has special cases, not worth further discussion right now. Next slide, please. This program works in the sense that we get back an augmented CPS data set with new columns that have the imputed industry and occupation for the early data that matches the category system used after 2000. So one consistent column for industry and another one for occupation, others for hours and employer class. We think these imputations are more accurate on a micro level, and we can check whether they have surprising effects on industry aggregates. The charts show just that the basic counts of time of employed or self-employed people are not much changed in this industry from what we get if we use a crosswalk. In other words, the new approach didn't cause any surprises in this case. We anticipate that there will be other industries where a meaningfully more precise estimate is possible than was possible previously because the industries will have been more sharply imputed. Next slide, please. The new imputations will need to meet more criteria than they now do. The micro-imputations don't necessarily produce results that match economy-wide data like the population census. Another kind of benchmark would be administrative. For something like the number of judges, we can bring in administrative data for where we know the right answer to how many judges there should be in the population.
1 minute.
There are other criteria that should be met. If the size of an occupation or industry jumps sharply from one year to the next, that's clearly a result of a classification change, not a change in the economy. Next slide. The random forest classifier can be tuned. The tree can incorporate more variables in each decision branch or fewer. There could be more or fewer trees. This is subject to computer time and memory limitations. After tuning, we want to match those macro benchmarks, and multiple or fractional imputation may help to cover small cases, and we can change thresholds. Next slide. So the random forest approach is working. It brings us some benefits. There's more to do to make it really usable for research and production. There are more data sets to use as input, and there are more data sets where imputations could help. In this audience, in this workshop, I'm interested in contact with anybody who's interested in occupation and industry coding and in tuning parameters to random forest models. So I'll put my contact information in the chat box. Thank you, that's all.
Thanks very much, Peter, and feel free to direct your questions to him there. Excellent. Next up, we have from our studio, Josiah Perry.
Hey, folks. Am I responsible for doing the slides? Okay, never mind. Here we go. Awesome. Thanks, everyone. My name is Josiah Perry. I'm on the customer success team here at our studio, and I am really fortunate to get to work with all of our government clients. Y'all prove to be unique in your challenges, and I'm learning a lot about them. Next slide, please. So I kind of want to first preface this by discussing the changing data science landscape. Next slide, please. So what we've seen over the past couple of years is that data science is becoming more and more central to production applications, right? We are moving beyond this need for just ad hoc reports and visualizations in dashboards. And in order to kind of enable data scientists to be more productive and succeed or excel, not just succeed, we need to equip them with production level tools. And one of the tendencies I've seen and noticed is that there's this large reliance upon IT to get anything from a proof of concept to a production type of content, right? So in order to succeed, I'm of the mind that we need to, we as in data scientists need to embrace some concepts from DevOps, right? If you're not familiar with DevOps, it's really just short for development operations. And that is just a fancy way of saying, how do we get things into a production environment quickly and safely, right? And I think the key thing to take away from that and from DevOps in the data science landscape is microservices. Next slide, please. So to kind of conceptualize what microservices are, I want to start with what's called a monolith. A monolith is this, think of your typical Shiny application or Plotly Dash or Streamlit application. It might have like 3 different components in it. It might be working with a data warehouse. It might be producing some sort of visualization or interactive visualization, or and providing model scoring from a machine learning algorithm you have. So all of these code, all of these functionality is embedded into just one massive application. So when you deploy the application, all the functionality is just contained in the code for this application. And this is called a monolith. Next slide, please. And microservices are really just a change in the way that we think about application design. So when we design these applications, we're going to break them up into their component parts. So you have that data warehouse component, the visualization, and the machine learning components. The idea with microservices is you take those unique and identifiable components and put those into production as their own pieces, right? And to be monitored and maintained on their own. And then your application design is just the integration of these 3 parts. And your application is really just gluing them together. Next slide, please. And I really think this quote is really phenomenal. It comes from it's related to the idea of the single responsibility principle in computer science. And it goes, gather together those things that change for the same reason and separate those things that change for different reasons. And just like best practices with Git commits, where you bundle together changes that are related to the same goal, the idea with microservices is that we isolate the processes that serve one goal. Next slide, please. And the question is, okay, well, I get the idea maybe that we should break things up into smaller bits, but how? Next slide, please. And APIs, that's how we're gonna do it. Next one. And you might be asking, what the heck is an API? You might have heard of it, you might have interacted with it, but you don't maybe not have a full understanding what that is. Next slide, please. In the TLDR, or the too long didn't read on APIs, is that API is just short for an application programming interface. This is just a fancy way of having machines talk to other machines. And when we talk about APIs, or when I'm talking about APIs today, I'm specifically referring to what's called a RESTful API. There are different things like SOAP APIs, but in most cases, you'll encounter what's called a RESTful API. These are APIs that use what's called HTTP, or Hypertext Transfer Protocol. This is the same idea of how the internet works. So I like to think of HTTP as this universal language that every programming language worth its salt knows how to speak. And since it's a universal language, it opens up so many doors for us. Next slide, please. To conceptualize an API, kind of think of it like a function, right? We have functions that have names and arguments, and then they take those arguments and do something. Like a function, APIs have parameters, which they have parameters which can be used similarly to function arguments to determine what comes out from that output. Next slide, please. So the current data science toolbox looks kind of like PDF reports, PowerPoint presentations, spreadsheets, interactive dashboards, etc. The issue here is that these are all limited to end user consumption, right? That's really good in most cases, but I think what we're going to be going to more frequently, and you might have already encountered the need to do, is to expand your toolbox to be a little bit more programmatic. Next slide, please. And the way we're going to do that is through APIs. Next slide, please. So why an API? Next slide. So some of the benefits, you might be able to intuit why I'm recommending APIs after I go through these. The first is that it's organizational. You are now being able to, by breaking apart an application into its component pieces, you are now just managing each thing on their own. So rather than managing 10,000 lines of code in separate subdirectories, you are just managing one application at a time. So smaller pieces of code are much easier to maintain. And you get like a side effect of being able to focus just on functionality, right? Whereas if it's built into a Shiny application, for example, you have to be considerate of things like interactivity and whatnot. And by breaking apart these pieces, you actually have better component monitoring, right? When you have just a single monolithic application, you are monitoring activity to that application. However, if you have things on their own RESTful APIs, you can monitor the API calls to each component, right? And when you build these microservices or APIs, you're actually reducing your future technical debt because you are building the infrastructure to recycle your code. You're no longer copying and pasting code from one project to another, and it's a really good benefit in that way. Another part of this is that you have better change management. So instead of, say you have to make a change to your data warehouse interaction because maybe some of the schema names changed, you don't have to push an update to the whole entire application and risk breaking it. At worst, you risk breaking the HTTP call to the API request to your data warehouse. So you have much better change management. Next slide, please. The next benefit, category benefits, are collaborative. I think these are the most important. There's a lot less friction in the tool handoff. What this means is that we can empower teams to use their preferred tool chain. You might have siloed teams where one team uses R, Python, JavaScript, whatever. And if all we're thinking about is API requests and not the safe software language, that means there's just so much less communication barriers in the way, right? If everyone's speaking HTTP, you don't have to deal with like using reticulate to call Python from R, RPy2, and vice versa, or if no one knows your language, right? That's
3 minutes.
Thank you. And I think the other benefit is that we can enable programmatic use of your services by other teams. Whereas if you're using things like dashboards, this requires user intervention. And I think one of the awesome parts here is now that you have API requests, you can just glue together everything, regardless of the stack that's underneath it. You can just start thinking about all the potential pipelines you can make. Next slide, please. And some of the signs that you might be ready to create an API are if you have redundant code, or if there are other teams that want to use your code, and particularly if those other teams do not know your language, it might be very useful to create an HTTP, an API. Next slide, please. And so how do you build an API? Next slide. So in the R world, there's a wonderful package called Plumber. This helps you build HTTP requests from functions. In Python, there are Flask and Fast API. I don't know much about it because I'm an R user. In JavaScript, there's Node.js and Express.js. The whole point is that they make RESTful APIs. Next slide, please. So how do you deploy an API? Next. In my world, I think of RStudio Connect. It's very simple. It's push button publishing, but this could be on-prem, however you want. Or you can use a service like DigitalOcean, or you can go the full DIY route and use Docker and Kubernetes and however you want. Next slide. So now I'm going to ask you, why just limit your stack to Shiny applications or Plotly or Streamlit? Next slide, please. When it could be any application or toolchain you want. You could be using Plumber, Flask, Streamlit, Node.js, Plotly, anything from SAS, data, anything that speaks HTTP. And next slide. Thank you. If y'all have any questions, feel free to email me. It's just josiah@rstudio.com, Josiah. I'm happy to chat and have a longer discussion about any topic data science related. Thank you. I think I hit that right on the time limit.
Yep. Thanks very much, Josiah.
Thank you.
All right. Next up, we have from the U.S. Census Bureau, Charles Coleman.
Hi, I'm Chuck Coleman. I'm a mathematical statistician, and my primary job is working on developing specifications for estimates from the Survey of Construction. Title here: Online Visualization of Survey of Construction's Price Estimates. I know some that may look like gibberish, but I will explain it. Next slide, please. I have to give the standard disclaimer. These are my views and not those of the Census Bureau, and it's been screened for disclosure avoidance. Next slide, please. So what I'll start by motivating this work. I'll define Windsorization. I'll determine the outlier, I'll show how to determine the outlier cutoff online, derive a SAS lesson, and wrap it all up. Next slide, please. So our motivation is that the Census Bureau's Survey of Construction has been using Windsorization, an outlier control technique, to mitigate the effects of high prices and small sample cells on price statistics. The small sample cells are reflected by high weights. Now, a Windsorization uses a cutoff value to determine outliers and replaces them with that value. Now, formerly, this cutoff value was pre-specified, and there was just no clear criterion, no documentation, nothing. Now, this cutoff is determined online during processing to minimize the estimated mean squared error. Next slide, please. Windsorization is an outlier-resistant estimate of your mean, what we call mu. Usually, it's two-sided. And it works by taking an input value y sub I and a cutoff value c. And if the absolute value of this y sub I is greater than that cutoff value c, we replace it with c times the sign of the original yi. Then we compute the average with the replaced data. And I'll be calling this Windsorized mean mu hat sub w. An important implication of this is that the variance is reduced, and this reduction increases as C decreases. And this is the basis for targeting MSE. Next slide, please. Now, the price data are all positive, so Windsorization becomes a one-sided process and introduces bias. The Windsorization rule simplifies that if yi exceeds the cutoff, you replace it with the cutoff value. Now, doing this as I said, introduces bias, and we have our usual, I mean, there's a whole bunch of math here, but important thing to note is mu hat naught is the usual survey estimator, sum of weights and prices divided by the sum of weights, and yes, WI are the survey weights, PI are the prices. And the estimated bias of mu hat sub W is simply the mu hat W, Windsorized mean that we've obtained less mu hat naught, which is the usual survey mean. So then the mean squared error calculation, or the estimated mean squared error calculation, becomes the variance of mu hat sub W plus the square of the difference of the two means, or the square of the bias. Next slide, please. And that gives us our optimization target. So we compute our yi's as being weights at times the prices, and then we find the C that minimizes the estimated MSE. And this we determined to be a multiple of 1,000,000, and this is a convention that we use. And we do this by using a grid search. We set our maximum equal to the maximum value of the y sub I rounded down to the nearest multiple of 1,000,000. Then we start at 30 million, which has some justification. So as arbitrary as it may look, increment that by 1,000,000 and stop at maximum. And for each of these steps, we use SAS's proc survey means to compute our Windsorized mean for C, for cutoff C, and its variance. And since we have those two, we can compute our estimated MSE and store it. Then we sort the MSEs to find the lowest one and output the corresponding C. We're done there. Next slide, please. Now here's a SAS lesson. This was really surprising. I found that proc survey means processes unused variables. I have to explain what's going on here. SAS uses data sets, and each data set consists of a matrix of variables and observations. Now, normally when you're doing things by hand, you only work with the variables that you want, like z equals x plus y. That just uses the three variables x, y, and z, and none of the others are touched. But for some reason, proc survey means processes all the variables in the data set, and that is costly. So the workaround is just to input only the necessary variables to proc survey means. This workaround may be useful for other SAS procs, especially for the ones that in the survey family. And there may be constructs in other languages that have similar behaviors. Next slide, please. So to wrap this up, selecting the Windsorization cutoff online produces our estimated mean squared error minimizing estimate of the sample mean of data of the same sign, which in this case positive. We use a grid search on a fixed grid. It's simple, but it's slow and not very precise. So you can always use a faster, higher precision search using a different algorithm, and there are loads of algorithms for that. And also avoid calling SAS proc survey means with unused variables. Probably should do that with other SAS survey procs and perhaps similar constructs in other languages. Next slide, please. If you want to see the code, it's in my repository there. One thing I should note that there is a SAS macro, which didn't get onto this version of the slides, called findcutoff.sas, which implements a macro find cutoff that does all the work. And of course, you can do this in other languages. And that pretty much is all I have to say. Thank you.
Thanks very much, Charles. And just about a minute to spare. Excellent. Anybody who wants to follow up can, Charles can let you know how to contact him in the chat. All right. Next up, from the University of Washington Technology and Social Change Group, we have Bree Norlander. Hi, Bree.
Hi, thank you. Okay, thank you, Mitchell. And welcome everyone to my lightning talk on E-rate funding, how I built a data pipeline in R from a scheduled R script on AWS to a Shiny dashboard. I'm Bree Norlander, data scientist with the Technology and Social Change Group at the University of Washington's Information School. This project would not have come to fruition without the ideas and resources of my colleague, Chris Joasis. If you would like to reach out to either of us about the project, please feel free to send either of us an email. I'm also pasting my contact information and relevant links from this talk into the chat. Next slide, please. First, a bit of context about the data. Libraries in the United States have access to discounts on internet and telecommunications services and related equipment through the Schools and Libraries program, which is commonly known as E-rate. E-rate is an FCC program designed to implement the universal service principle that all Americans should have access to communications services. To receive discounts, eligible school and library organizations submit an application either individually or as part of a system or consortia to the Universal Services Administrative Company, or we'll call USAC, which administers the E-rate program. USAC provides application and decision data on a Socrata open data platform with download and API options for retrieving data, allowing us and really anyone to analyze the data and provide insights into how libraries are using the E-rate program. Next slide, please. So Chris Joasis and I identified a need within a group of users for quick access to aggregated data about libraries using E-rate. And as an avid R user, I wanted to stand up a nice shiny dashboard for others to see the data in table format and with charts where applicable. This is when I encountered the data pipeline problem. Socrata has an API for pulling data, and you can see Josiah's earlier talk for more information about APIs, which is a better solution to getting just the right data than, say, downloading a CSV. But depending on the API query, pulling the data from the API can take up to and significantly longer than 30 minutes. This will not work for a Shiny application backend. Also, the data sets are updated daily and require some transformations before displaying in Shiny. Next slide, please. So after lots of web searches and trial and error, the solution I ended up with was running a virtual machine on AWS with a cron job that runs an R script every weekday. The data sets created in the R script are then pushed to an AWS S3 bucket, and using the AWS S3 R package, pulled directly from S3 for use in the Shiny dashboard. And while I would like to show you how to do all of these steps, I can't talk that fast. So instead, I will provide slides with some recommended resources, screenshots of my work, and tips and hints I learned along the way. Hopefully you will come away from this talk with the resources, terminology, and tips that will get you started on a similar project. Next slide, please. I set up a virtual machine using AWS EC2. Why AWS? Because our group already had an account and I was familiar with its services. There's no reason you couldn't do this in Azure or Google Cloud or another service, for example, if that's what you prefer. I used a pre-built Amazon Machine Image, or AMI, from Louis Aslett, which you can find on the second link on this slide. It comes with R and RStudio, though I just use R from the command line in my virtual machine. Next slide, please. Next, I created an R script on my virtual machine. I built this script by trial and error on my own machine in RStudio. I then copy-pasted it into a text editor on the virtual machine. You could just as easily import it from your machine. This is a screenshot of the very beginning of the script with 3 tips for you. The first tip is to record the time at the start of the script and at the end of the script. You will want to keep tabs on how long it takes to run. The second tip is to write out your data sets to S3 as you make them. If necessary, you may need to remove them as you go depending on the size of the machine you chose. And the third tip is to use print statements to output what has happened and when while your script is running. You'll thank yourself later. At the end of the script, I also run an RM command to remove all the locally stored data sets. Next slide, please. Now that your script is written and stored on your virtual machine, you'll want to run it at certain times and days. In my case, I wanted to run it early in the morning every weekday. To do this, I created a cron tab. You might also hear these called cron jobs. Here is a screenshot of my current cron tab. Getting this set up in just the way I wanted took a lot of trial and error. And that's okay, that happens all the time in my work. Here also are some resources I found particularly helpful in setting this up. It runs my script every weekday at 12:10 UTC, outputs a log of the script output, and sends the log to an S3 bucket. I can then check the log easily if the script doesn't appear to be functioning properly. Next slide, please. If your R script and your cron job are working, you have everything you need to grab data from your S3 bucket within your Shiny code. However, like me, you may have a bigger EC2 instance than the free tier allows. This means I'm charged based on how long the instance is running. I need it to turn on and off automatically, so I only pay for the time I need. This is where I use AWS Lambda and Amazon CloudWatch events, or as it's now called, Amazon Event Bridge. And guess what? It's basically another cron job. You can see the cron expression on the screenshot to the right of the slide. It also outputs the next 10 trigger dates and times, which is very helpful to see that you have set up your event correctly. The link I've included in the slide walks you through the whole process. You can also use the AWS Instance Scheduler, for which I've included a link, though I haven't personally used that. Next slide, please. So then you're all set to grab data from your S3 bucket and use it to display information in your Shiny dashboard. You can use the AWS S3R package and set up your environment variables to access your bucket. You'll have data that is up to date and transformed the way you want it for your Shiny application. Here you can see the link and a screenshot of the Shiny dashboard I am running. Please feel free to explore the dashboard further on your own. I have included a link in the chat. Next slide, please. And that is the end of my talk. Thank you to everyone, and I hope to hear from some of you. Please feel free to reach out.
Excellent. Thanks so much, Bree. Feel free to connect with her in the chat there. And we are ahead of schedule so far. Next up from RTI International, we have Lauren Warren. Hi, Lauren.
Hi. All right. Okay, thanks. Hi, everyone. So I'm Lauren. I am a statistician and data scientist. I do some project management, several different jobs, and I've been with RTI International for about 12 years now. So today, well, you know, it's really interesting hearing the various talks that we've already heard today and that what we have coming up this afternoon, how variable a lot of these areas in which we're all working are, and it's just fascinating to me. And this is, I wanted to present something today that is a little different than what I normally, kind of the tasks that I normally do or I have done for the majority of my career. But it's something that I find, just interesting. And so as a little bit of a background, I do a lot of work on very big, kind of complicated government survey projects, and where we'll have many teams, and we're all doing, working toward these, bigger deliverables that will ultimately go, be sent to our client, and then other deliverables that will be released to the public. But we're all kind of working, I wouldn't say it's siloed because we do communicate a lot, but our granular detail of our everyday activities is really managed within each of our tasks, or our teams, I should say. So what we were kind of charged with, well, and I will also say that kind of in the age of, in technology advancements and all kinds of different tools that we have at our disposal that help to kind of make our work more efficient, there's this expectation that we really need to make, kind of optimize our processes. And for those of you who work on some of these projects that are kind of like considered to be like legacy projects that, may have, iterations annually and have been around for a really long time, it's not all that often where we're given the opportunity to really take a step back and kind of look at the process, as a whole and figure out how can we make this more efficient, because it's typically pretty expensive and labor intensive to do that. So we were given some funds, my team was, and we were wanting to figure out how can we most efficiently utilize these funds to get kind of the biggest bang for our buck in the end, in terms of time to deliverable, time to delivering the data. And for us, and this could really be applied to a lot of different types of projects, but for us, for today's example, I'm talking about a project where we get data are collected, and then it goes through a number of teams or processes, editing, imputing, analyzing the data, and then ultimately the data are put into, or there are analysis tables and reports and things like that, other deliverables in the end. So this was our problem. How do we figure out where to invest these funds? Because everything is so complex, there are so many different dependencies that it's really almost impossible to say, yes, let's put it here, because that may speed that little part up, but it may mean that there are other pieces, there are other teams working on other factors that will ultimately go into the deliverable that may not be able to capitalize on those funds being spent in that area. So you can go to the next slide, please. All right, so this is, kind of talked a little bit about the problem we were having. So we decided to help us reach the solution of where we're going to invest these funds. We held an idea-a-thon. We called it an idea-a-thon. It's similar to a hackathon, but really our focus was on what different ideas teams might come up with to kind of make different processes more efficient. But we had some staff involved in this process that were very familiar with the inner workings of the project, and then we had other staff that were less familiar, but that may have had a more broad perspective on different tools that might be available to us and things like that. And I don't have time to talk through the details of how we went about the idea-a-thon on a daily basis, but it lasted a couple weeks, and we met periodically, and in the end, we talked a lot about pain points, how we might mitigate those pain points. But there was this overwhelming realization in the end that we needed to map out, as painful as it might be, every little detail, kind of from at a variable level, going from data collection all the way through to the final products. And we needed to get all those dependencies that some teams had, where they some teams completed theirs and passed some variables on to the next team, and then more work was done on those, and it kind of passed it back and forth. We need to have all of that in a very granular schedule. So I will say that there are so many different open source software possibilities. I know a lot of you here work with, there's just a wide variety of software being used. We did not use open source software. I do a lot of my programming in SAS. We had that available. We also have Smartsheet available to us now. So that was how we developed our solution, but I'm interested to see in the chat or through email later if others had have other ideas on how you might do something similar with open source software. Next slide, please. All right, so like I said, we had the teams enter all their kind of nitty-gritty information into Smartsheet. We could do that collaboratively all at the same time. That was very nice. And then we exported the data, and then we could read that into SAS. And the great thing about the reason why I wanted to do that is because I'm more familiar with SAS, but also because we wanted to be able to push a button, have this whole process macrotized, and in the end, we have about 800 to 900 different, tables or, reports. It's just this huge project. We wanted a Gantt chart to be output to kind of visualize the process for every single one of our deliverables. And obviously we're not going to do that. We're not going to create one in Smartsheet 800 times. And there were some other complications anyways, because our schedule ended up being, thousands of lines long. So to pinpoint which lines, ultimately fed into a specific data table, analysis table, that was a very complicated, it was more complicated than it seemed like it would be. So we set up some code that, got all of that information, it selected all the lines that we needed in the schedule. We had some other options. We assigned different colors to the different teams that were working on them to help us visualize this. And so then what I'll show you now is, so we have, I think I've covered everything here. Next slide, please. What I'll show you now, this is just a little code I just wanted to include a little bit of the code, but this is really just the Gantt chart code. This is something that I didn't even know existed before I was trying to visualize this process. And so this was kind of neat for me just because I've never used SAS in this way. So it's kind of cool. And so this just shows you a little bit of how, and it required some data manipulation to get the data in the format that the Proc Gantt needed. But there's documentation here. But this is, and also I will say that Proc Gantt is very powerful. There are lots of different options you can use. I don't use them, but this is a very simple example of using Proc Gantt. Next slide, please. So this is kind of, and I've changed a lot of the labels here to be kind of just general labels, but this is the output that is an example of some of the output that we got out of this. And this is just for one of the tables. Like I said, there were like 900 of these that we got, but we could also summarize those differently. And there are some other details too that I really won't go into today. But this was neat because you can see these are, it was color coded by team. Next slide, please. And then, so we were able to kind of pinpoint, here are some areas where it doesn't seem like maybe we might not need this much time. Maybe we should invest some time in these, invest some of the funds in trying to simplify or make these processes more efficient. Next slide, please. And we kind of focused in on a couple of them. And so this is an example. I think this specific table was finished on, the end of March. And then next slide, these kind of go a little quicker. So, we could take those two lines that we ended up wanting to focus on. We could spend some funds on the weighting process and then also on the specific edited variable line. And we could invest in those two areas, and then we could make some changes in Smartsheet, export a new Excel file to see what the impact would be, run the same program, same SAS program, get a bunch of Gantt charts in the end. And then next slide, please. And then, so you'll see here that this was, running the exact same program. We can get, Gantt charts in the end, and that shows you the revised schedule. And for this specific table, we cut it, we reduced the time by a month. So it was end of February, I think February 27th. And so what's important about this, or what was helpful, was that there were so many dependencies that we really couldn't capture all that well, that seeing it visually, there were just so many moving parts that seeing it visually in something like this was really helpful for us. And I thought this was just a neat usage of SAS that I had never really seen. But I'm interested to hear, it looks like we have some comments in chat, but I'm not sure how much time we have, but I'm interested to hear if others have had similar successes in using other software options. That's all I had today. I think it's the last slide.
Thanks very much, Lauren.
Mm-hmm.
All right, excellent. We have just one more presentation left, and we are a few minutes ahead of schedule. All right. From the USDA's National Agricultural Statistics Service Information, also known as NASS, we have Luca Sartore. Hi, Luca. I see we have the slides up. Hi, Luca. Are you with us?
switching over to panelists. Oh, he should be here soon.
All right, excellent. Yep, feel free to.
Hello, do you hear me now?
Hi, Luca.
Yeah. So good afternoon, everyone. Today I'm going to present a crop classification program that we have developed to get a map of the country eventually, and with uncertainties, and all this process is gonna performed in Google Earth Engine, which is a cloud-based platform where we can do spatial analysis and produce these maps. Next, please. Here I have a disclaimer. Next, please. So the crop land data layer is a product that NAS produces every year using remote sensing images. And it shows cultivated areas and what kind of crop is cultivated in. This product, because it evolves with time, it provides also crop rotation pattern. And it has been used for different applications within NAS. Next slide, please. The objective for this study are actually creating these type of maps way early in the season when crop has been just planted or just emerged. And to do this, we are trying to use remote sensing with higher resolution to be able to identify these crops probably in a better way that early in the season. And we also do not have administrative data to train our model. So before performing all these analysis, we need to figure out how to get a process that is able to provide high classification accuracy, even without the use of these administrative data. Further on, to assess the quality of our classification, we have developed these uncertainty layers to identify areas that may have like some problems related to misclassification or that are really challenges to model. Next slide, please. The classification approach that we applied in this case is based on bootstrap method. So for each iteration, we take a different sample. And on these samples, we classify a model. And from these models, we get classifications, results, and we take the mode of those classes. So the class that's most frequent is going to be our final classification. However, by doing this, we need to use a prediction frequency to evaluate the predictive distribution. Next slide, please. So we have uncertainties that have been developed based on the predictive distributions, and these entropies, there varies between zeros and ones, where zero it's a value that presents where we tend to reproduce the same class several times over our bootstrap iterations. And this value is close to 1 when the predictive distribution is closer to a uniform, discrete uniform. Next, please. The algorithm is basically the following. We have within the bootstrap to prepare our data, so we include crop rotation patterns and remote sensing images, and we sample them. Once we have these training data sets, we perform a random forest training classification. And based on those results, we produce our map and the uncertainty layer as well. If we have FSA data that are administrative within our secure environment, we can also assess the accuracy of those classification results. Next, please. In Illinois, we did this early season crop classification with the following settings. So we just iterated 16 bootstrap resample. We use the maximum number of data points allowed by Google Earth Engine in our training set, and we train a random forest with 16 trees at 90 meter. We use 90 meter because it tends to produce more stable results with the 10 meters later on when we classify. And for each tree, we use half of the initial training points for classifying, producing these classification trees within the forest. The whole process of producing these maps for Illinois it took 18 hours, and this also leverage on parallel computing of the cloud system. Next slide, please. So these are some examples in the first row of the classification performed in June with its correspondent uncertainty layer. We see that the highlighted circles for areas that have higher entropies, and therefore we see on the left how these fields, they might be higher than in terms of noise or different pixel that the model had much harder time to find or predict a better class. Other areas that have higher entropies are those that are urban, but those areas for our analysis are not relevant. And if we compare these results with the end of season CDLs, where we use all the full imageries from the satellites, we see there are some differences, they are minor, between the early season in June and the end of season CDL, and between the 10 meter and the 30 meter version, where the 30 meter is the official published on NAS website. We see that they're very comparable, and the only differences are basically on the resolution on these images. Next, please. Because we have internally these administrative data that we can consider as ground truth from the Farm Service Agency, we can estimate our accuracies of the classifier. So we produce like overall accuracy from 2017 to 2019. And these are larger than 78%. The producer accuracy for corn, these are related to corn fields that actually have been planted with corn, and 78%, no, let's say more than 30 and 83% are actually correctly classified, and soybeans fields are more than 74% are actually correctly classified. We have user accuracies. Those are related to the classification field, and the classified fields as corn, those are more than 78% actually planted with corn, and the predicted soybeans fields more than 77% were actually planted with soybeans. Next, please. So in conclusion, we can say that identification in June is kind of difficult to do because we miss part of the phenological cycle where there is the best information to discriminate between corn and soybean fields or other fields that have been planted with different crops. However, because we can leverage on this uncertainty layer, we can also identify areas that has more problem through the classification. We noticed that producing historical crop rotation pattern at 10 meters by using the full resolution with the end of years to provide the information as covariates, that allows us to improve our classification results. And the preliminary results show the potential of these early classification maps for current and future NAS operations. Some references on the next slides. And the next, I have my contact information. And thank you. If you have any questions, please reach out.
Fantastic. Thanks very much, Luca.